Have you ever stopped and wondered how your computer does it? How it seems to have this bottomless pit of memory, ready in an instant. I mean, you can have dozens of tabs open, a game running, and somehow it all just works. Well, what if I told you that whole seamless feeling is actually one of the most brilliant tricks in all of modern engineering?
Okay, so let's really dive into this. I mean, seriously, how does your computer pull it off? How does it feel like it has this infinite instant memory? You've got tons of tabs open, maybe a huge game running, a video playing in the background, and it just works. So how is that even possible? Well, the answer is, it's all a grand illusion. Yep, a really carefully constructed performance that's designed to hide a fundamental, kind of inconvenient truth about the physical world. So, to really understand this illusion, we've got to first get a handle on the basic problem it's trying to solve. And you know what? It all comes down to a classic engineering trade-off. And here it is, the iron law of memory. You can have fast memory, or you can have big memory, or you can have cheap memory. But, and this is the crucial part, you absolutely cannot have all three at the same time. See, super fast memory, it's incredibly expensive and you can't get much of it. And that huge, cheap storage, painfully slow. This right here is the dilemma every single computer architect has to deal with.
Okay, to really get a feel for just how huge these differences are, let's use an analogy. It's a great one. Let's imagine that a single operation for the computer's brain, the CPU, takes exactly 1 second. Now let's see how long it would take to get data from all the different places it might be stored.
All right, so if the CPU needs data from its own little notepad, its super fast internal memory, we call that the L1 cache. It gets it in that 1 second. Bam! Basically instantaneous.
Okay, but now, what if the data isn't in that little notepad? What if we have to go a little further out and get it from the main system memory? You know, the RAM? Well, all of a sudden, that 1 second wait just became 1 minute and 40 seconds. Woo! You can already feel the system starting to lag, can't you?
But hold on, what if the data isn't even in RAM? What if we have to go all the way out and fetch it from a traditional spinning hard drive? That 1 second operation would now take, get this, 1.5 months. Months! Waiting months for a single piece of data is, well, it's completely impossible. So this is the real question. How on earth do engineers hide this absolutely massive delay?
And that brings us to the first part of the magic act, cache. This is the sleight of hand, the trick that creates the illusion of pure, unadulterated speed. You see, the entire idea of caching is built on a really simple but powerful observation about how computer programs actually behave. It's called the principle of locality. And all that really means is that programs tend to reuse the same bits of data and instructions over and over again in a really short amount of time. And this principle kind of has two flavors. First, there's temporal locality. That's just the idea that if you just use something, like say a counter in a loop, you're probably going to use it again really soon. Then there's spatial locality. This one says that if you use a piece of data, you're probably going to need the data that's stored right next to it, like when you're reading through items in an array. Caches are basically designed to make bets on these two behaviors happening.
So here's what a cache is. It's a small, super-duper fast, and yeah, expensive piece of memory that sits right next to the CPU. Its whole job is to keep a copy of what it thinks you'll need next from that much slower main memory, and it's making that guess based on the principle of locality. When it bets right, and that's what we call a cache hit, the CPU gets its data instantly. And just like that, the illusion of speed is maintained.
Okay, so if caching is the trick that creates the illusion of speed, our next trick, well, it's even more ambitious. This is virtual memory, and it's what creates the truly mind-bending illusion of size.
I mean, seriously, think about this for a second. How can your computer with maybe 8 or 16 gigs of actual physical RAM run a massive 20-gig game or some complex video editing project without just instantly crashing? The numbers just don't add up, right?
The solution is another incredibly clever layer of illusion called address translation. And here's the core idea. Your program, the game you're playing, it doesn't actually know or even care where its data is physically located in the real hardware. So here's how the trick works. First, your program asks for data at what's called a virtual address. Think of it like a fake address in its own little private world. Then, the operating system steps in. It looks up that request in a special map, a page table. This table is like a translator. It turns the fake virtual address into a real physical address on your RAM chips. But here's the real kicker. If the data it needs isn't in RAM at all, The OS cleverly and quietly swaps it in from your much bigger but way slower hard disk. And the best part? Your program is completely oblivious. It has no idea any of this is even happening.
So you've got these two incredible illusions working together in harmony to make your computer feel absolutely limitless. But, just like any magic trick, sometimes it can fail. So let's talk about what happens when the illusion shatters.
You ever have that moment where your computer just grinds to a halt? You know, the lights are blinking, maybe you can hear the hard drive just churning away, but absolutely nothing is happening on your screen? If that sounds familiar, you've probably experienced something called thrashing. It's what happens when the system gets caught in this awful loop, spending all of its time just managing the illusion instead of doing any actual productive work.
And this is the deadly spiral of thrashing. First, the system runs critically low on actual physical RAM. To make space, it starts frantically swapping these little chunks of memory, we call them pages, back and forth to the slow hard disk. So now the CPU is just stuck, waiting and waiting for the disk to catch up. But to make any progress, it needs more data, which causes more swapping, and you see where this is going. The whole thing just seizes up. The magic show is officially over. And by the way, this is exactly why adding more RAM is often the single best upgrade you can make for an older computer. It just gives the system more breathing room, stopping this whole deadly spiral before it can even get started.
So, this grand illusion, this beautiful hierarchy of caches and virtual memory, has been the engine powering computing for decades. But our demand for data is just growing at an insane rate. We're talking massive AI models, 8K video, you name it. The pressure on this system is becoming immense, and all this leaves us with one really fascinating question. As our data needs continue to explode, what's going to be the next great memory illusion?